Loudspeakers interfering again. Two small speakers, S1 and S2, are positioned at a distance d equals 1 meter from each other, as shown in the diagram. The two speakers are each emitting a constant 800 Hz tone, and the sound waves from the speakers are in phase with each other. A student is standing at point O, which is a distance of 5 meters from the midpoint between the speakers, and hears a maximum amplitude sound as expected. Assume that reflections from nearby objects are negligible. Use 340 meters per second for the speed of sound. Part A. Calculate the wavelength of these sound waves. B. The student moves to point H and notices that the sound intensity decreased as she was moving, but then increased to a maximum at point H. Calculate the shortest distance the student could have moved to hear this maximum amplitude. Identify another location on the line that passes through O and H where the student could stand in order to observe a maximum. Justify your answer. D. The student now moves back towards point O and notices that the sound goes away at a point between H and O. Where is she? Explain your answer. E. How would your answer to B change if the two speakers were moved farther apart? And F. How would your answer to B change if the frequency emitted by the two speakers was decreased? Justify your answer. Calculate the wavelength. Use the wavelength frequency wave speed relationship right over here. F is equal to the velocity of sound over lambda. Substitute in our numbers, and we get a wavelength of 0.425 meters. Calculate the shortest distance the student could have moved to hear this maximum amplitude. The student was at the 0th order maximum, m equals 0, at point O. Point H is the first order maximum, where m is equal to -1, or the next point where the student would hear a maximum sound amplitude. Use the formula for the distance from O along the y-axis for maximum amplitudes where m is -1. So its y is m lambda L over d. Here's our m. Here's the wavelength we calculated. Here's L, which is the distance between the speakers and the y-axis there. And d is 1 meter. That's the distance between the speakers. And you get y is minus 2.13 meters. So that tells you it's down here. Identify another location on the line that passes through O and H where the student could stand in order to observe a maximum. Justify your answer. So maximum amplitudes are reached for m is equal to 0, plus or minus 1, plus or minus 2, etc. The m equals 0 maximum is at y equals 0, and the m equals -1 maximum is at point H, where y is minus 2.13 meters. Continuing along the minus y-axis, further maxima are found as integral multiples of minus 2.13 meters. So y2 would be twice that, so that's 4.26. y3, 3 times 2.13. y4, 4 times. And in general, y sub m is equal to minus m, which is a number, it's not meters. Meters is over here, times 2.13 meters. Maximum amplitudes are also found along the plus y-axis up here as mirror images of the amplitudes along the negative y-axis. So these are the numbers from the previous slide, except what? They had a negative in front of them. This time they're positive, so you have some symmetry there. The student notices that the sound goes away at a point between H and O, somewhere in here. Where is she? Explain your answer. The student was at the 0th order maximum, m equals 0, at point O. Point H is the first order maximum, m is equal to -1, or the next point where the student would hear a maximum sound amplitude. Between points O and H is the first order minimum, where m is equal to 0. At this point, the student would not hear any sound, so somewhere in this area. Use the formula for the distance from O along the y-axis for minimum amplitudes, and this time m is going to equal 0. Here's our formula. We plug it in, and the m goes away because it's 0. And now why did we write two numbers here? Well, that's answered over here. Since m can equal 0, or plus or minus 1, plus or minus 2, plus or minus 3, etc., that gives negative and positive values for all the integers, right? You have a plus or minus 1 here, plus or minus 2, except 0. So we need to look at the picture and assign a negative to y as it is below 0.0. So you're going to be right over here at y is negative 1.06 for your first minima, and then on the other side, your first minima would be y equals plus 1.06 meters. How would your answer to B change if the two speakers were moved further apart? Justify your answer. So what are we doing here? Moving them further apart, so D will increase. So the distance to the first and subsequent maximum amplitudes would decrease as the distance is inversely proportional to the speaker separation. So as this gets bigger, what happens to Y? It decreases. How would your answer to B change if the frequency emitted by the two speakers was decreased? The distance to the first and subsequent maximum amplitudes would increase as the distance is directly proportional to the wavelength of the sound and inversely proportional to the frequency. So here's the equation we've been dealing with. You replace lambda with velocity over frequency. And what have we done here? We've decreased frequency, so that means y will increase.